Hey, Calculus. Welcome to section 9.4, day 2, Improper Integrals, and the very last section that we're going to cover here before your Chapter 9 test. Keeping that in mind, maybe we should just get started right away. So in the climactic scene of Raiders of the Lost Ark, the Nazis recapture the Ark of the Covenant and plan on opening the vessel. Ark of the Covenant, you would remember, is the place where the original tablets that held the Ten Commandments were supposed to have been placed. So they're trying to open the Ten Commandments, I guess. And this says an infinity of souls emerges from the Ark, appearing at first angelic and then demonic. And the Nazis are swiftly punished. Yeah, we like that. Punishing Nazis. How does an infinity emerge from a finite volume? That's a calculus question. Can an infinite region contain finite area? And we already saw that, yes, it can. We've seen limits used to evaluate integrals that extend to infinity as an upper and lower limit, but what about integrals that have a vertical asymptote, an infinite discontinuity? So we're going to try the same technique that we used for infinite limits with improper integrals that are not infinite. At least they don't go to infinity. So we have this integral from 0 to 1 of 1 over root x. And where is this discontinuity? Well, I can see really plainly that if I put a 0 into this function, I'm going to create 1 over 0, which is a problem. Let's take a look at that as a graph. You can plainly see as x approaches 0, this region extends to positive infinity on the left side, which is still an infinity, but in a different way than the way that we looked at before. Now we have a vertical infinity, and with the previous lesson, we were looking at a horizontal infinity. First, substitute a for this point of discontinuity and rewrite the integral. That's not a big deal. We did that in the last section. A to 1 of 1 over root x dx. And then now it says to evaluate this integral. So let's go ahead and evaluate this. This is equal to the integral from a to 1 of x to the negative 1/2 dx. Our antiderivative is 2 root x, and when we substitute, we get 2 minus 2 root a. Very nice. Now, if 0 to 1 of 1 over root x converges, then it should be equal to the limit as a approaches 0 from the right of the integral from a to 1 of 1 over x. Basically, let's take this limit. The limit as a approaches 0 from the right side of 2 minus 2 root a, I'm sorry. And this isn't a big deal because we can directly substitute a. There's no reason why a can't be 0. This just gives me 2. So does this integral converge? Yes. What does it converge to? Well, the integral from 0 to 1 of 1 over root x dx converges to 2. So again, a region that is infinite has a finite area. What about this one? We've got from 0 to 3 of dx over x minus 1 to the 2/3. Where is this discontinuous? And looking at this, this looks like if I substitute 2 into the denominator, I'm in big trouble. So this is discontinuous at x equals 2. Let's rewrite this as two integrals using our properties of integrals, which you may or may not have forgotten. So this is the integral from 0 to 2 of dx over x minus 2 to the 2/3 plus the integral from 2 to 3 of dx over x minus 2 to the 2/3. Okay, using techniques, we can evaluate each of these integrals using limits. So let's find our antiderivative first. Our antiderivative here, this can be easily viewed as x minus 2 to the negative 2/3 power. Negative 2/3 plus 1 is 1/3. So our antiderivative is 3, x minus 2 to the 1/3 power plus constant. That's going to help us greatly because now we got the integral from 0 to b plus the integral from a to 3 is going to be equal to our antiderivative from 0 to b plus our antiderivative from a to 3, which is 3 cube root of b minus 2 minus 3 cube root of negative 2 plus 3 cube root of 3 minus 3 cube root of a minus 2. Now we're ready to compute our limits. So we have the limit, or the integral from 0 to 3 is equal to the limit as b approaches 2 from the left of 3 cube root of b minus 2 minus limit as a approaches 2 from the right of 3 cube root of a minus 2 plus 3 cube root of 3 minus 3 cube root of negative 2. And I'm going to do a little bit of alteration here because the cube root of negative 3 of negative 2 is the same thing as negative cube root of positive 2. So that's one thing which you can do with cube roots. Don't do it unless you know what you're doing, of course. And we can evaluate these limits now. There's nothing wrong with directly substituting, even if it's a one-sided limit. If I substitute 2, this gives me 2 minus 2, or 0. So this goes to 0. And if I substitute 2 in this one, I also get a 0. So when I evaluate this, this looks like 3 cube root of 3 plus 3 cube root of 2. And that is a pretty darn good answer. And I'm looking at this and I'm realizing that I made a mistake way back over here. This was supposed to be 3 minus 2. So this over here should have been 1. So this looks like 3 plus 2 cube root of 2, which I'm going to stick with. We're going to switch gears a little bit here, and we're going to see, working with a partner or two, we're supposed to evaluate dx over x to the p for a value between 0 and 1. And I'm looking at this and thinking, hey, you know what? There's some problems here because these are actually supposed to go from 1 to infinity. So let's do these from 1 to infinity. Let's pick a number between 0 and 1. Maybe let's pick 1/2. So we got the integral from 1 to b of x to the negative 1/2. That's equal to 2 square root of x from 1 to b. And that's equal to 2 root b minus 2. Now let's apply our limits, and we can say the integral from 1 to infinity of x to the, let's write that as a quotient again, 1 over x to the 1/2 dx. That's going to be equal to the limit as b approaches infinity of 2 root b minus 2. Now, of course, 2 root b is going to go to infinity, so this does not exist. So, does not exist. How about when p is equal to 1? What is the integral from 1 to infinity of 1 over x to the first power dx? Well, that's going to be equal to 2 root, p is equal to 1. That's going to be equal to, well, my antiderivative is natural log of x. So this is going to be equal to the limit as b approaches infinity of the natural log of b minus the natural log of 1. Now as b goes to infinity, this also goes to infinity. So this also does not exist. And what about the last one? Some number bigger than 1. Well, we could pick 2. Why not 2? So the antiderivative, or the integral from 1 to b of 1 over x to the negative 2, 1 over x squared dx, that's equal to negative 1 over x from 1 to b, which is going to be equal to negative 1 over x to the b plus 1 over x. Sorry, 1 over 1. And this should be 1 over b. Okay, so then the integral from 1 to infinity of 1 over x squared dx, that's going to be the limit as b approaches infinity of 1 over b negative plus 1. And that's equal to 1. So when we try p equals 2, this converges. So what does this lead us to believe? Well, this says that if we integrate from a constant to infinity of dx over x to the p, it's going to converge if p is greater than 1. And it's going to diverge if p is less than or equal to 1. And this is really important for us to remember. I'm going to reference this again in the future a lot. So please try to think about this. The integral from some constant a to infinity of 1 over x to the p dx converges for p greater than 0, and it diverges if p is less than or equal to 0. Very important for us to remember for the future. Now, there's basically 3 things here that we need to talk about in this section. We've gone over the first 2, and then this is going to be our third one. So we got to switch gears yet again. And we're supposed to draw 2 functions, and we want to make sure that f is always bigger than g. So let's call this, actually, let's change this graph just a little bit. Yeah, let's do this. Let's call this f of x, and let's call the other one g of x. Now, g of x needs to stay over f of x, and I'm not super satisfied with this one also. Yeah, this is a little better. We'll call this one g of x. So if I take a look at these 2, which of those has more area? Well, I think it's pretty obvious that the area associated with g of x is going to be bigger than the area associated with f of x, because g of x is bigger. Now, keep this in mind. The area for g has to be bigger than the area for f. If we have 2 functions where f is smaller than g, and if I say g converges, let's say the area under g is equal to 5. What do I know about the area under f? Well, the area under f has to be something less than 5. Or, the way you want to think about it is the area under f has to be something. So, if the bigger function converges, then the smaller function has to converge as well. If the bigger function converges, the smaller function converges. And then let's work the other way around. What about the smaller function? What if the smaller function converges? Now take a look over here. If I tell you the area under f is infinite, what does that tell you about the area under g? It can't be less than infinity, so it has to be infinite as well. So if the smaller function diverges, then the bigger function must also diverge. Now the other two cases are what we call inconclusive. And let's see, what if the bigger function, what if g diverges? Does that tell you anything about f? Not really, because f could still equal any number that's less than infinity. So if the area under g is infinite, the area under f may or may not be infinite. It could just as easily be equal to 3. Other way around, what about if the area under f is equal to, let's say, 2? If this area is 2, does that mean that the area under g has to be, well, it just has to be bigger than 2, right? So it could be 5, it could be 9, it could be infinity. So the only two of these cases which mean anything would be if the bigger function converges and then if the smaller function diverges. Keeping that in mind, let's get to our important ideas for this section, the last set of important ideas for this chapter. So there are two things here, and the first one is improper integrals. And this just tells you that if you have a place which is infinite, either on the left or the right endpoint of the integral, you can go ahead and turn it into a limit problem instead. And then this is the one that we just went over, which is if you have a function that's bigger than the other function, if the bigger function converges, a smaller function also converges. And if the smaller function diverges, then the bigger function is going to diverge. So that's actually a lot of stuff we went over. We didn't even talk about the p functions, where the integral from some constant to infinity of 1 over x to the p dx, that's going to converge if p is greater than or equal to 0, and it's going to diverge if p is strictly less than 0. So those are the three big concepts that we did. Let's get to question, check your understanding. Number 1. Show that this is a diverging function, or evaluate or show this is diverging. Now, where do we have problems with this integral? It looks like if I substitute 2, I'm going to have problems here. So we are going to first find our antiderivative. What is the antiderivative of dx over 4 minus x squared? Well, u substitution won't work. So I think the plan here is to use partial fractions. So we've got 1 over 4 minus x squared. That's going to be equal to a over 2 plus x plus b over 2 minus x. Or 1 is going to be equal to 2 minus x multiplied by a plus 2 plus x multiplied by b. If we let x equal -2, we can show that a has to be 1/4. And if we choose x equals 2, we can show that b is also equal to 1/4. We're going to evaluate the integral from 0 to b of dx over 4 minus x squared. That's the same as 1/4 the integral of 1 over 2 plus x plus 1 over 2 minus x. Be careful with the second one because the u substitution is going to make the antiderivative negative. This is 1/4 natural log of 2 plus x minus natural log of 2 minus x. We don't need the absolute values since we know that our values of x's are going to be from 0 to 2, and none of those will give us a negative natural log. That simplifies to 1/4 natural log of 2 plus b over 2 minus b minus 1/4 the natural log of 1. Of course, the natural log of 1 is 0, so we're really only left with this first term. Let's put our limits. The integral from 0 to 2 now of dx over 4 minus x squared. That's going to be equal to the limit as b approaches 2 of 1/4 2 plus b over 2 minus b. Let's analyze this second limit. As b approaches 2, the numerator clearly goes to 4, but the denominator is going to go to 0. Now 4 over something that goes to 0 is going to reach positive or negative infinity. In this case, it's going to reach positive infinity since our values are going to be less than 2. Remember, we're approaching 2 from the left side of it. So like 1.9, 1.99. So we have a negative, positive over positive infinity. This is going to go to the natural log of positive infinity, which goes to infinity. So this is a divergent integral. I don't know why I felt so unsatisfied about that, but it is a diverging integral. Comparison test. Use comparison test to show whether the integral from 1 to infinity of dx over 5 plus e to the x converges or diverges. So first thing, have a hypothesis. Do you think this converges or diverges? And I'm looking at the denominator here, and I'm saying that denominator is going to go big really fast, which means the function's going to get small really fast. And if you remember from looking at our graphs earlier in the past lessons, we saw that if the function approaches the x-axis really quickly, if the function decreases really quickly, we're going to have a converging function. So I'm going to guess this is going to be converging. So that's my hypothesis. Number 2, simplify the integrand into something integratable or integrable. If you think that you're going to have a function that converges, then you want to find a larger integrand. And if you think the function, if our hypothesis is diverges, then we're going to find a smaller integrand. So we think this is converging, so we got to make this integral larger, and we can do that by just saying dx over e to the x. Okay. We've made the denominator smaller, which makes the ratio bigger. Let's integrate this. So the integral from 1 to b of e to the negative x dx, that's going to be equal to negative e to the negative x from 1 to b, which is equal to, what is this? E to the first power minus e to the negative b power, which is e minus 1 over e to the b. Whoops, 1 over e minus 1 over e to the b. So my infinite integral from 1 to infinity of 1 over e to the x dx, that's going to be equal to the limit as b approaches infinity of 1 over e minus 1 over e to the b, which is equal to 1 over e. So we're looking at a converges. So if our bigger function converges, what does that say about the smaller function? Well, it says that the smaller function has to converge as well. Conclusion, since e to the x is bigger or equal to 1 over 5 plus e to the x, and the integral of 1 over e to the x converges, that means that the integral from 1 to infinity of 1 over 5 plus e to the x, that also has to converge. Now, I know that comparison thing kind of makes people nervous because we are not directly evaluating integrals. We are just inferring their properties based on other integrals. So how do you know what to do? Well, you can do what I did, and if you have constants being added to a denominator, you can just get rid of them. Same thing with multiples. If you have 5 over e to the x, just get rid of the 5 and do 5 over or 1 over e to the x. Basically, try to simplify the integrand as much as possible and see if that simplified integral is converging or diverging. I'm sure we'll have more practice with this in the future, but this is the end of our Chapter 9 experience. Good luck on your test, and I'll see you guys later.